Hey, and welcome to this Neptune Snackable session, which is going to talk about GraphRAG. Topic's been around for quite a little while, but this is something really close to my heart. Absolutely love generative AI, how it can be incorporated and integrated with graph. So really excited to talk about the topic today, and also how you can actually start building a GraphRAG solution quickly on Amazon Neptune. So let's dive straight into it. So what are we going to talk about today? So enhancing generative AI with graphs. So what are the types of use cases we actually see combining graphs and Gen AI together? Next, we're going to explore sort of GraphRAG. How does it differ from traditional RAG in a sense? And then finally, actually talking about the ways, the solutions that already exist, the toolkits that give you the ability to actually build your own GraphRAG solutions using Amazon Neptune. And then I want to cover some next steps, lots of stuff to share with you. So really excited. Let's get cracking. So enhancing generative AI with graphs. So we kind of like see two very distinct patterns between the way Gen AI can actually integrate with graphs. So first of all is like open domain question answering. So this is where you've already got a graph and you're effectively saying, okay, I'm going to allow my users to run natural language queries across the entire graph. They can literally ask for anything. Good reasons for that, for doing things. It provides flexibility. It provides flexible accessibility as well to the graph data that for users that potentially aren't familiar with graph, aren't familiar with the underlying graph schema. When should you not use that? Well, it basically provides direct access to your entire data. If you were ever doing like an open domain Q&A application, you really want to put guardrails in to ensure that new data, they're not just creating new data in your knowledge graph, or they're saying, okay, give me everything, query back everything, which is going to overload an API or anything like that. Next, we've got defined domain question answering. So this differs slightly in the fact that you're still allowing your users to ask a natural language question to your graph, but you're actually using LLMs to first identify the context of the question. So what type of questions they are asking, and then extract elements from that question to put into template queries. Now, this approach, again, provides accessibility to the graph data, but in a much more tightly controlled manner. And this is especially useful when the domain is much more complex and it's non-trivial to query without sort of an expertise. When should you not use it? Well, the fact is that you've got to define these templated queries. So if you've got loads, that leads to maintainability issues. And there's going to be someone's going to need to be knowledgeable about the graph, about the domain, in order to actually write these template queries. So next we've got sort of the side of the graph generation. So the previous was sort of like text to graph, effectively. So you've got a knowledge graph. You're asking the LLM to query your knowledge graph. Now we're asking the LLM to create the knowledge graph. So knowledge graph generation, really, how does this work? Well, you provide a file, you provide a data source to the LLM and say, okay, create me a knowledge graph from this. And it's going to perform things like entity extraction. It's going to perform sort of analysis on those entities, understand the context in which they're all connected, and then it's going to effectively create nodes, create entities within your graph. Now, this is great because it allows you, effectively, it's a much more of a hands-off approach to creating a knowledge graph. You're not having to manually create these types of entities. The thing being, I suppose, with this, like anything, is there's a significant amount of trial and error involved. While technologies are getting much still in that, and certainly the things that I'll be talking about today are creating sort of very opinionated models. You're still going to need some sort of level of domain knowledge to be able to verify that the knowledge graph has actually been created properly. And then finally, we have graph enhanced RAG or GraphRAG. So this is kind of like where you're still building, you're still creating your graph, but you're actually now leveraging the power of graph traversals in addition to things like similarity lookups and things like that, to provide a more comprehensive, more accurate answers. And we'll talk a little bit more about this sort of the approach to GraphRAG. So as we've seen, GenAI plus graphs is not always GraphRAG. So what is GraphRAG? So this sentence is actually quite important to understand. So sometimes the most relevant information to answering a question is not the closest in meaning. So what does that mean? So let's break that down. Let's break RAG down into its component parts and also integrate some with GraphRAG as well. So first of all, we have got vectors. Now, vectors are essentially a mathematical representation or encoding of a something. Now, that something could be a word, it could be a picture, it could be a soundbite, video, it doesn't really matter. But fundamentally, vectors are used by machine learning, by AI, to process and understand information. In RAG applications, they're used to identify similarity between objects. So, for example, dog and cat are similar in the vector space because they are related to the same family of words, for example, animals or pets. Now, graphs, as we discussed early on, are used to identify connections between data. Now, using the example of cats and dogs, these might have connections with something like a ball or a toy that aren't directly similar, but are still related to the core concepts. So further to this notion, RAG solutions primarily focus on things that are similar in the vector space. So this is generally known as like vector similarity search or cosine similarity and top K. However, where this approach fails is when you need to retrieve all relevant information. So information that is like unrelated to the search term, or in fact directly opposite the search term in the vector space, will fundamentally be ignored. So how do we get around this? Well, using graphs can provide us with several different methods of connecting information that is related. So for example, parent-child relationships, cause-effect, semantic similarity. We can actually use the graph to model out all these different types of relationship in order to interpret the data better. So just a quick overview of some graph terminology before we dive any deeper. So firstly, we have nodes. Now, these represent entities or like things within our graph. Like an entity can be something in the real world, it can be transient, virtual, it doesn't matter. It's an actual thing, like a person. Nodes can also have properties which represent key value pair attributes associated with that object. Next, we have edges. Now, edges are used to determine the type of the relationship between nodes. So two nodes can have multiple edges between them that represent both an instance of a relationship. So, for example, the number of times I've signed up and subsequently cancelled my gym membership, as well as the type of relationship itself. So edges too can have properties. These include like weighting properties, or for example, metadata, such as like the date and time of when a relationship was created or when it ended. So let's look over a GraphRAG example to identify really the differences between traditional or vector-based RAG and GraphRAG, and see how that actually affects the accuracy of a response. So we have a RAG application that has stored information relating to a specific company, and this company, Example Corp, it sells widgets. They've partnered with Any Company Logistics to deliver those widgets to the UK at Christmas. And here we can see that information along with sales trend data. And we can see that there will be huge demand for these widgets over Christmas in the UK. So as a business, I want to understand what my sales prospects are for Example Corp in the UK. Now, If we were to query that using like traditional RAG, vector RAG, we can see the RAG application has identified similar information to my question. So we can see example corp there in both objects here. So we can surmise that sales are going to be good. Hooray! Fantastic. That's excellent. Okay, so what does this actually look like from a GraphRAG approach? Well, first of all, by using the graph to connect related but dissimilar information, we can get a more holistic view of what the sales prospects will be for example corp. So here we can see that any company logistics is actually cutting shipping times by using the fictitious canal. So this is actually a net positive benefit. However, we can also see that the very same canal is blocked, causing delays. So it's this connected information specifically associated with the delays relating to the fictitious canal that provide us with additional context in order for AI to generate a more accurate response. So whilst it immediately looks like we've got huge demand, fundamentally we can't provide a supply for that demand. So sales are likely to be negatively impacted. So how does GraphRAG fundamentally work? Well, the first key step is the build maintain step, where multiple foundational models are used to first generate a vector embedding of a given chunk, to extract specific entities and facts from a chunk, identify entities based on known or given synonyms. For example, AMZN is the same as Amazon, is the same as Amazon LLC, etc., things like that. From here, those sources, those chunks, entities, facts, etc., they're all stored in the graph, connected by contextual relationships derived through extraction process. For example, things like same as or related to. Now, the next key steps are the retrieve and generate steps. Now, GraphRAG works by performing an initial vector similarity search to identify information that is similar in the vector space. So this is important because both RAG and GraphRAG effectively start in the same way. However, from there, graph queries will be run to traverse 2 or potentially 3 hops out from these nodes to actually understand about all the connected yet dissimilar information. So finally, the foundational model will generate a response based on the retrieved graph objects. Now, that includes the prompt, that includes the question, and the context in which the graph objects are connected. So that was all the theory-based stuff. Like, how do you go about building a GraphRAG solution using Neptune? Well, we have a couple of primary solutions that I'm going to discuss. So first of all, we have Amazon Bedrock knowledge bases. So this is a fully managed GraphRAG solution. And secondly, we've got the GraphRAG Toolkit. So this is an open source Python-based toolkit that provides functionality to choose between vector stores as well as embedding, extraction, and response models. So it really depends on which one you use, depends on sort of your use case. So let's talk about the initially Bedrock knowledge bases for GraphRAG. So Amazon Bedrock knowledge bases offers a fully managed GraphRAG feature with Amazon Neptune. So it creates Amazon Neptune analytics graph behind the scenes, and it provides capability to actually create your graph data model. Through Bedrock knowledge bases, you can ingest data from multiple sources to create a generic graph data model that describes the different entities and relationships between them. So GraphRAG automatically identifies and leverages relationships between entities and structural elements within documents ingested into knowledge bases. So what this does, it means it really provides and enables a more comprehensive, contextually relevant response from a foundational model, particularly when the information needs to be connected through multiple logical steps. And also better cross-document reasoning capabilities, allowing for more precise and contextually accurate answers by connecting information across various sources. So you're not just using a single source approach to this. And this effectively further enhances accuracy and minimizes hallucinations. So this is what the GraphRAG data model actually looks like. Initially, you're going to create through the chunk creation embeddings generation. Effectively, documents are broken down into smaller, manageable chunks. vector embeddings are generated from these chunks to encode their semantic meaning. So what do they actually? What do these pieces actually mean? What do they relate to? And then from that, entities extracted from the chunks. They serve as edges, linking related chunks, which are the nodes, which you can see here, based on shared entities and context. The resulting graph, as I mentioned, is stored in Neptune Analytics for efficient query and traversal. Let's now talk about the GraphRAG Toolkit. So the GraphRAG Toolkit is a Python-based toolkit library that integrates with Llama Index to combine GenAI with graphs. So it provides the ability to automatically create a graph from unstructured data. Now, it uses similar constructs as the Bedrock Knowledge Base's graph data model to create a lexical graph representation of the ingested unstructured data. Under the hood, it uses Llama Index components to build the graph, as well as integrate with foundational models during the various AI processing stages, like generation of embeddings, entity extraction, and then subsequently the response models. So the lexical graph data model is effectively broken into 3 tiers. So we've got the first one, lineage, which is the blue nodes you can see. So this defines where a specific chunk of information comes from, i.e. the source document, and also which chunk or chunks it is connected to. So by having this relationship model, we can actually provide a foundational model with the context for it to understand what proceeds or precedes a specific chunk, and from which source an actual chunk actually came from. Next, we've got summarization, and these are the green nodes. So this tier is made up of topic, statement, and fact nodes. So topics represent centralized themes such as Amazon Neptune Database Service or Neptune Database Technical Features. Statements are directly connected to topics. You can see here the belongs to relationship. And they provide support for known pieces of information, such as Amazon Neptune supports open cipher query language. Now, facts are then derived from a statement in a manner that identifies both the connection and the type of fact. So, for example, Amazon Neptune supports open cipher. So, capitalizing like the supports keyword. So, entity, then the final tier is the entity relationships. So this is the red node. So the final tier is made up of entities or the things identified as part of a fact. Now, they're actually modeled as triples based on the context of a fact. And you can see like entity can be a subject or it can be an object of a fact. Now, using the previous example, so things like Amazon Neptune supports open cipher, both Amazon Neptune and open cipher are in fact entities. However, the subject of the fact is actually Amazon Neptune, and open cipher is the object of the fact, with the relation being supports. So in addition to entities that are actually part of multiple triples, they're also connected to each other to actually help determine the context between them. So when should you use sort of managed versus open source GraphRAG? So from a fully managed perspective, the scalability and performance is optimized really for any scale enterprise applications within AWS. It's a fully managed service. So as you'd expect, security and compliance, it has integrated with AWS, so integrated security protocols. In addition, from an operational perspective, you're really looking at reduced development operational burden with AWS support and maintenance. So you're not having developers continually tweak the prompts or things like that. You're really utilizing that fully managed service approach. Now, from an open source perspective, it's high. What are some of the positive things about this is its high customizability of it. You can choose different models for different sections. You can for different AI processes. You can change the batch load. You can batch sizes. You can change the number of workers. You can really tweak it for the compute for the specific use case that you're working on. You can host it across multiple accounts. So it provides a lot of customization. In addition, open integration, you've got choices for your graph store, so you can use Neptune database and Neptune analytics. You can lots of choice for your vector store as well. Connections between like Neptune analytics for both graph and vector, Amazon Neptune database for your graph, and then Amazon OpenSearch serverless for your vector store. PG Vector, lots of different options around that. So if you're more comfortable, if you've got experience working with different vector stores, there's potential that the toolkit will immediately work with that. So next steps, just wanted to share with you some developer resources. So we've got the GraphRAG Toolkit. We've got our public docs on how to actually build a knowledge base using Bedrock, and also Neptune MCP, which is a video that we're going to be producing shortly as well. Some videos that you might want to be interested in as well: discovering graph data modeling using generative AI and diagram as code, as well as integrating LLMs with LangChain. And then finally, we've got some blogs. So introducing the GraphRAG Toolkit, and also introducing Amazon Neptune plus MCP. I also want to share with you while I'm here the QR code around the GraphRAG Toolkit. Lots of information there, lots of example and notebooks that you can use, which I'd highly recommend for that. And then with that, I would like to thank you very much.